So I want to revisit very, very briefly antiderivatives, mainly so I can give some notation to it, and because antiderivatives are going to be used by us most of the time when we want to evaluate definite integrals. So if I have a function f, we've talked about how the derivative is denoted either as f prime by Newton's notation or df dx using Leibniz notation, but we didn't give a notation for antiderivatives. And typically for an antiderivative, the practice is to capitalize the function. So if my function is h of x, its antiderivative would be capital H of x, which would be 5x. And then remember the plus c, because I don't know what this constant is. And if I take its derivative, derivative of 5x is 5, derivative of c is 0, that checks out. And remember, when you find an antiderivative, you should always take its derivative to check if it's right. So that if I want the antiderivative of little f of x equals x, that'd be capital F of x be equal to x squared plus c. But then when I check this, derivative of x squared would be 2x. I don't want that 2 in front, so I need a 1/2 to cancel it out. And then antiderivative of little g of x would be capital G of x. I have a 2, which I'm just going to hold on to. Antiderivative of x squared would be an x cubed. But when I check that, if I bring the 3 down, that'd be a 6x squared. I don't want it to be 6, so I'm going to divide by the 3. Then antiderivative of 1 over x would be the natural log of x. And then my plus c. The reason I do this is because of what's called the fundamental theorem of calculus. And I'm going to introduce it here in part, because the fundamental theorem of calculus, or FTC, kind of fundamental to calculus, and it comes in 2 parts. We're not going to worry about part 1 right now. I'm going to save that for next section. Part 2 is what I want to focus on, because that's what I want to practice right now, which is the idea that you can use antiderivatives to evaluate definite integrals. And what it is it says if I have a definite integral from a to b of f of x, find the antiderivative of f of x. This notation then means I'm going to stick the b in first to the antiderivative, then stick the lower bound a into the antiderivative and subtract them. So to do this, if I have the integral from 0 to 2 of 5 dx, or 5, with respect to x, I need the antiderivative of 5, which would be 5x plus c. I'm then going to plug the 2, so I have the 5x plus c from 0 to 2. Plug the 2 in first, which gives me 10 plus c. Plug the 0 in second, so 0 plus c, and subtract them. 10 minus 0 is 10. C minus c is 0, and 10 is my answer. Now please note, the c's canceled. In a definite integral, this will always happen. So what that means, very helpfully for us, is we can ignore the plus c in definite integrals. Now please note, it is only for definite integrals. We will learn about what are called indefinite integrals. We have to have the plus c for those. We will learn about what's called an improper integral. We need the plus c in those. But for definite integrals, we can ignore plus c because in the subtraction, the c will always cancel out. So if I now look at the next example, I need the antiderivative of x, which would be 1/2 x squared. I can ignore the plus c. If you want to put the plus c, it hurts nothing, but I can ignore it because it's a definite integral. So I have 1/2 x squared from 1 to 3. I plug the 3 in first, so I have 9/2. Subtracting, plug in the 1 next, 1/2, and that gives me 4. You can probably start to see why we really like this method of evaluating definite integrals. Because then when we get to shapes where we don't have any handy formulas for area, like parabolas, I can use definite integrals to evaluate it. So antiderivative of 4 is 4x, minus antiderivative of x squared is 1/3 x cubed, from -1 to 3. Plug the 3 in first, 12 minus 9. Plug the -1 in second, which is -4 plus 1/3. And I'm not required to simplify, so this is my definite integral's answer. If I go to a few other examples here, again, if you want to pause the video, give these examples a try, and then play the video to check your answers, that's great. Otherwise, you can just follow along. We did not talk about a division property for definite integrals because there isn't one. But notice I can rewrite that so that it's a constant multiple. X over 5 is the same as 1/5 x. So I can think of this as the integral from -1 to 3 of 1/5 x. Well, the antiderivative of 1/5 x will be 1/10 x squared from -1 to 3. Plug in the upper bound first, so 9/10, minus plugging in the lower bound, which is going to be 1/10. So I get 8/10. If I need the integral from -1/2 to +1/2 of 1 over the square root of 1 minus x squared, this is one of our inverse trig functions. That's the inverse sine from -1/2 to +1/2. Well, that means I need the inverse sine of 1/2 minus the inverse sine of -1/2. Inverse sine of 1/2 is going to be positive pi over 6, minus inverse sine of -1/2 is negative pi over 6. So I get pi over 3. Then integral from 0 to 2 pi of cosine of x. Antiderivative of cosine is sine. This is one especially I would recommend. Make sure you're double checking. Derivative of sine is positive cosine, so that works. From 0 to 2 pi. So I have the sine of 2 pi minus the sine of 0, which is 0 minus 0, or 0. And this actually should make sense because cosine is periodic, and its period is 2 pi. It's symmetric above and below the x-axis from 0 to 2 pi, so the area above the x-axis has the same magnitude as the area below it. They cancel each other out.